In the alkene chapter, one of the addition reactions that we learned, in fact it was the first addition reaction we learned, was hydrohalogenation. And this was where you added a hydrogen and a halogen onto an alkene. And we saw two versions of it. One was the hydrogen and the halogen all by itself, and the other had the hydrogen and the halogen combined with a peroxide. So that was ROOR. These capital R's are any carbon chain. And the per means a lot. You have a lot of oxygens there in the middle, two oxygens bonded to each other. Now the difference between these is that in just regular hydrohalogenation, it's Markovnikov addition. So the hydrogen goes on the less substituted carbon, and the bromine, so the hydrogen goes on the less substituted carbon, and the bromine would go on the more substituted carbon. So Markovnikov addition. On the other hand, we saw that when you add peroxides, you get anti-Markovnikov addition. So in that case, the hydrogen adds to the more substituted position, and the bromine adds to the less substituted position, actually. So we've seen these two reactions before in the alkene chapter. Now, in the alkene chapter, we did learn the mechanism for this top one. It was one of the first mechanisms that we drew for the addition reactions. But we never learned the mechanism for this peroxide. And that's because for the anti-Markovnikov addition in the presence of peroxides. And that's because that involved radicals, and we hadn't built up a toolbox and a vocabulary for talking about and understanding the behavior of radicals at that point. So we mentioned at the time to notice this. It's a useful recipe that you can use as a chef, but we didn't give an explanation for why it was anti-Markovnikov addition. The explanation for why it is anti-Markovnikov addition will become clear in this next exercise, where we draw the mechanism for that reaction. You can see we're doing hydrohalogenation in the presence of peroxides, ROOR. And we know that when we do that from the previous chapter, we know that what we'll get is anti-Markovnikov addition. The hydrogen will add on the more substituted carbon, and the halogen, in this case bromine, will add on the less substituted carbon. We know that from the perspective of synthesis, but here they're asking for the mechanism. How does that happen? Well, it happens through a radical mechanism. And as always with radicals, the story of the reaction happens in three parts. A beginning, that's an initiation step. A middle, that's going to be a propagation step. And an end, that's going to be a termination step. So a beginning, a middle, and an end. Initiation, propagation, and termination. Okay, well, what will be the initiator? How will the radicals get created? The radicals will get created by the peroxide. You'll have this R, so that's any carbon chain, bonded to an oxygen, bonded to another oxygen, bonded to another carbon chain. And the bond between the oxygens is very unstable. And you can see why carbon is so special. Carbon forms stable bonds to itself. Other elements, like oxygen, do not. All it takes is a little bit of heat. You don't even have to shine ultraviolet light on it. Just a little heat and the peroxides break apart and create two radicals. This one electron will go onto one oxygen, the other electron in the bond goes onto the other oxygen. This should look familiar from previous exercises. This homolytic cleavage, which creates two radicals. And in this case, the two radicals will be two oxygens. So that bond breaks. We get a radical on each of the oxygens, and so we end up with 2 radicals. So that's the initiation step, the creation of radicals through homolytic cleavage. And in this case, we're making them just with heat. Okay, now for the propagation step. And there are going to be 2 steps for the propagation. So, in the first propagation step, forgive me, actually, before we get to the propagation step, okay, let's organize it this way. We've done the initiation step, we've created the radicals. Now we're going to do the propagation, and there are actually 3 propagation steps total in the way I'm going to organize this. So in the first one, we take one of the oxygen radicals that we made, and we're going to react that with the hydrohalogen that we have. So we have a hydrogen, in this case the halogen it's bonded to is the bromine. So this is going to be a hydrogen abstraction. This radical is going to steal the hydrogen from the bromine. So it will contribute 1 electron to a bond, the hydrogen will contribute 1 electron to the bond, the other electron in this hydrohalogen bond will go onto the bromine to create a radical there. So what we have after that first propagation step is the bond between the hydrogen and the bromine breaks. One of the electrons goes onto the bromine, and the bromine has 3 other lone pairs. The other electron goes to form a bond to the oxygen. So you now have a full bond between the oxygen and the hydrogen. Okay, so in that propagation step, we turned one of the oxygen radicals into a bromine radical. Okay. So far, what the steps we've drawn already will always occur, no matter what the carbon chain is. So far, the carbon chain has not played a role. The carbon chain enters in the second propagation step. So I'll copy this carbon chain down. Oops, let me try this. We'll have a methyl group there and then a pi bond. Okay, so the bromine radical that we formed is going to add onto the pi bond. It's going to bond to the less substituted carbon of the pi bond. So it's going to steal one of these pi electrons. And you might remember why. In terms of stability, it's easier to break a pi bond than it is to break a sigma bond. Sigma bonds are bonds where, or that's the first bond you ever form. That's where you have uninterrupted overlap between 2 orbitals. So for example, if I have 2 s orbitals here, you can see how they are, how they overlap, and the overlap is not interrupted at all. Compare that with a pi bond. A pi bond is every bond you form after the first bond. In a pi bond, you have 2 parallel p orbitals. And so the orbitals do overlap, but the overlap is interrupted. And so the bond is weaker because it doesn't overlap as much. The overlap is what creates the bond. You can see in sigma bonds, you get much better overlap, uninterrupted overlap, compared to the pi bonds. So if we're comparing these, the first bond you ever form is the sigma bond, and every bond after that is a pi bond. So when this bromine radical approaches this carbon, it steals one of the electrons from the pi bond. So it's going to create a new bond. The bromine adds 1, the pi bond adds 1, and the other electron in the pi bond goes on to the more substituted atom in the pi bond. That's why the bromine is adding on to the less substituted one. So that will form the more stable, more substituted radical. So when you do that reaction, this pi bond breaks, one of the electrons goes onto this tertiary carbon, the more substituted carbon, to give you the more stable radical, and the other electron pairs up with an electron from the bromine to form a new bond. So that would be our second propagation step. So in the first propagation step, the oxygen radical created a bromine radical. In the second propagation step, the bromine radical breaks the pi bond and forms a new bond to the less substituted carbon to give you the more substituted radical. In the third propagation step, this radical reacts with a second molecule of HBr. So you'd have that, you would have HBr, and this radical is going to rip that hydrogen off. It's going to be a hydrogen abstraction. So let me move this over just a little bit. This electron will add, that carbon will add one electron to the bond, the hydrogen will add another. The other electron in this bond will go on to bromine. And what you end up with is this bond breaking, one of the electrons going onto the bromine. That bromine also has 3 lone pairs. And the other electron going to form a bond between the hydrogen and the carbon. So you can see at this point, the carbon chain is done reacting. In fact, in this anti-Markovnikov addition, this hydrohalogenation in the presence of peroxides, the carbon chain only participates in the second and third propagation step. It does not participate in the initiation step, and as we'll see, it does not participate in the termination step either. The bromine adds first onto the alkene, creates the more stable radical at the more substituted position, and this is the reason why it's anti-Markovnikov. The bromine adds to the less substituted carbon so that the radical can form on the more substituted carbon. And then once you have that radical, it steals a hydrogen from HBr to give you your final carbon chain product. But we still have a bromine radical, and that leads us to the termination step. All of these previous steps, the initiation step and the 3 propagation steps, don't just happen with one molecule, they happen with hundreds of trillions of molecules. And so you're left with hundreds of trillions of bromine radicals at the end of these steps in your flask. So they end up combining with each other and stabilizing each other, canceling each other out. One of the bromine radicals donates 1 electron, the other bromine radical donates another electron, and so you have a coupling step in this termination. So you have the 2 bromines that were radicals bonding to each other. And so that's the termination step here. And that will always be the termination step for the radical addition of HBr to an alkene. So, this first initiation step and the first propagation step are always the same. The termination step is always the same. The only thing that ever changes is the second and third of the propagation steps. That's where your radicals interact with the carbon chain to accomplish the anti-Markovnikov addition of H and Br, where H goes on the more substituted carbon and Br goes on the less substituted carbon. Okay, so let's walk through that same mechanism for 2 more radical additions of HBr to an alkene, to 2 different alkenes, to build up muscle memory and to just build confidence in seeing these patterns. So in this next one, here is our alkene. We see HBr and hydrogen peroxide, well, not hydrogen peroxide, just a peroxide, ROOR, and we know that what we're going to get is anti-Markovnikov addition of H and Br. The hydrogen will go on the more substituted carbon, and the bromine will go on the less substituted carbon in the double bond. But how does that happen? That's what we're trying to explain in this exercise. Well, in the first step, the initiation step, so this happens through a radical mechanism. Radical mechanisms have 3 steps, beginning, middle, and end. The beginning is called the initiation step, and in that step, the peroxide breaks apart, always. So the bond between the 2 oxygens is not stable, heated up a little bit, and it breaks up into 2 radicals. Once you have those 2 radicals, you're ready to do the propagation step. Now the propagation step has 3 parts. This is the middle of our reaction. And the first part is always the same in these radical addition reactions. The oxygen radical that we formed does a hydrogen abstraction. It steals a hydrogen from HBr. And the other electron in the bond to the hydrogen snaps onto the Br, and you produce a bromine radical. So the oxygen radical steals a hydrogen and an electron. That gives you this new bond here between the oxygen and the hydrogen. The other electron in the bond between the HBr becomes a lone radical on the bromine. Okay, so that always happens in these radical reactions. You'll notice the carbon chain has not made an appearance yet. In the second step, the carbon chain appears. So I'm going to copy this carbon chain in. So that's our carbon chain. The bromine radical that we made in the first propagation step rips off one of the pi electrons. And that's going to form a bond between the bromine and the carbon, one of the carbons in the pi bond. And it's going to connect to the less substituted carbon so that you can form a radical on the more substituted carbon. So the bromine will contribute 1 electron to the bond, the pi bond will contribute a second, the other electron in the pi bond will snap back onto the more substituted carbon in this carbon chain. So here, the pi bond will break. One of the electrons will go onto the more substituted carbon to give us the more stable radical. And the other electron will combine with the radical from the bromine to create a new bond between the carbon and the bromine. So that's the second step. We add the bromine onto the pi bond. Second of the propagation steps. Then we have the third propagation step. In the third propagation step, we take the radical we formed in the second step, and we react it with a second molecule of HBr. So the one radical we have here, this unpaired electron, is going to rip a hydrogen off of this molecule. It's going to form a new bond to the hydrogen. It will contribute its 1 electron, the hydrogen will contribute 1 electron, the other electron in this bond will snap back onto the bromine. So the result will be that this bond will break, one of the electrons will become a radical on the bromine, and the other electron will pair with the radical that existed on the carbon to form a new bond between that carbon and the hydrogen. Notice that at the end of that third propagation step, we have a bromine radical. And at this point, we have added the H and the Br onto the pi bond. And it is anti-Markovnikov addition. The hydrogen is on the more substituted carbon, and the bromine is on the less substituted carbon. We're left with this bromine radical. So we've finished the middle part of this story. We have the beginning, the initiation step, the middle, the propagation step, and now we have the very end, the termination step. The termination step for these reactions is always the same. In the propagation step, what we're left with at the end is a bromine radical, and as hundreds of thousands of these molecules undergo this reaction, we're left with hundreds of thousands of bromine radicals. And those can start pairing up. When they do, they each contribute one electron to create a bond, and that stabilizes the radicals. As the unpaired electrons pair up, you terminate the reaction because you destroy the radicals, or you don't have radicals anymore. And so that is the last step, the end of this radical reaction with this carbon chain. So that's the mechanism for the radical addition of HBr to an alkene. Now let's do that one more time. This time with this alkene here. Now you see an alkene, you see HBr in the presence of peroxides, ROOR, and you know that that's going to be anti-Markovnikov addition. So you will add a hydrogen to the more substituted carbon, and a bromine in this case, that's your halogen, to the less substituted carbon, anti-Markovnikov addition. So from the perspective of synthesis, that's what the product is going to look like. But how does that happen? It happens through a radical mechanism. And radical mechanisms have three parts. They have a beginning, a middle, and an end. An initiation step where you form radicals, a propagation step where one radical changes places, and then a termination step where two radicals pair up. The initiation step for this radical addition is always the same. You take the peroxide, the bond between the two oxygens is unstable. All you have to do is heat it up, and it'll break apart and give you two radicals. So that's the beginning of the reaction. Now that you have your radicals, you can start the story of the radical reaction. That happens in the middle. The middle is the propagation step, or the propagation. And the propagation of this radical addition of HBr to an alkene has three parts. In the first part, the oxygen radical that we made from the peroxide always steals or abstracts a hydrogen from HBr. The other electron in the bond between the hydrogen and the halogen goes onto the halogen, in this case the bromine, to give us a bromine radical. So we have this ROH. Anytime you have a carbon chain bonded to OH, it's called an alcohol. So we have an alcohol, and then more importantly, we have this radical. Okay, so far our carbon chain has not been involved at all. These steps so far are universal for the mechanism for the radical addition of HBr to an alkene. Then in the second step, we take our bromine radical and it reacts with the carbon chain. So the carbon chain makes its debut entrance. So I'm going to draw that carbon chain. And I'm going to draw, it's going to react with our most reactive species, the bromine radical. Now, the bromine radical is going to rip an electron away from the pi bond. So it's going to add to the less substituted carbon of the pi bond so that a radical can form on the more substituted position. The more substituted radical is more stable because it spreads the radical out through hyperconjugation, as we discussed in a previous video. So the bromine donates one electron. The pi bond, the carbon, donates another electron, and the other electron in the pi bond goes onto the more substituted carbon in the alkene. So here, you end up with this bond breaking, you form a radical on that carbon, and you have a new bond between this bromine and that carbon. Notice that you have a tertiary radical here. It's one of the more stable radicals. Okay, so we've added the bromine and we've added it onto the less substituted carbon. So that's the second of the propagation steps, and then we have a third propagation step, where we take the radical that we formed in the second step and it reacts with a hydrogen bromide molecule. It rips the hydrogen off of that molecule. The bromine has 3 lone pairs. So here, this radical is going to bond to the hydrogen. It will donate 1 electron, the hydrogen will donate the other, and the second electron in this bond will snap back onto the bromine. So what you create here is, first, this bond breaks. One of the electrons goes onto the bromine and creates a radical. The other electron combines with the radical electron on the carbon to create a bond between the carbon and the hydrogen. Now, we're left with a bromine radical that's still reactive, but notice what we've done. These were the 2 carbons in the double bond. We've added an H and a Br across it, onto them. The Br has gone onto the less substituted carbon, and the hydrogen has gone on to the more substituted carbon. That's anti-Markovnikov addition. So those are the 3 parts of the propagation step, and what we're left with are bromine radicals. Well, that sequence of steps that we just drew doesn't just happen with one molecule, it happens with hundreds of trillions of them. And so we have hundreds of trillions of these bromine radicals in our container. And they can start pairing up until they're all gone. So this is the termination step. It ends the story of this radical reaction. One bromine radical contributes 1 electron to another bromine radical, which also contributes an electron. Together, those electrons create a bond. And so that's the termination reaction. And so, in this radical addition of HBr to an alkene, we finally explain why hydrohalogenation is anti-Markovnikov in the presence of peroxides. You create the peroxide in an initiation step. The peroxide steals a hydrogen from HBr and creates a bromine radical, and the bromine radical adds first to the molecule. It adds on the less substituted position, anti-Markovnikov, so that a radical forms on the more substituted position. That's the more stable radical. The radical steals a hydrogen, and ultimately the bromines pair up to terminate the reaction. So hopefully this video helps a little bit with thinking through and drawing these radical additions of HBr to an alkene.